speaker is Haojia Sun. Haojia Sun. I tried to practice this and have probably failed.
You're good.
Who will tell us about gradual verification for smart contracts?
Hello. Hello. Hi, everyone. Good afternoon. My name is Haojia Sun, a senior undergraduate student from Shanghai Jiao Tong University, and I'm delighted to share our ongoing work with you about gradual verification for smart contracts. So this is joint work with Kunal, Jane Paul, and our advisors Jonathan Aldrich and Jenna. Great thanks to all of my collaborators. So first of all, I want to talk about why our work is of great importance. We all know that the smart contracts are self-executing programs on the blockchains, and they facilitate secure resource transactions among mutually untrusted parties. And therefore, if these contracts have vulnerabilities, it could result in significant financial losses. I'm sorry, I lost my mouse, I think. Just give me a second. Sorry about that. I think I lost my mouse. Okay, cool. Here it is.
We don't see your screen anymore.
Oops. Let me check. Sorry about that. So I just talked about the vulnerabilities, and it may cause the huge financial losses if there have bugs in the smart contracts. So actually, the three properties of smart contracts highlight the importance of the verification. So firstly, it is the immutability. Once the smart contract is deployed, it cannot be changed. And this means that the bugs in the smart contracts are irreversible. And secondly, transparency. The code and operations of all the smart contracts are visible to everyone. While fostering trust, if the errors are present, it becomes straightforward for others to identify the bugs and initiate the attacks. And thirdly, automatic execution. The smart contracts operate without human intervention when meeting predefined conditions. And if there are issues with the smart contracts, they might execute incorrect operations without notice. And thus, it's really critical to verify the smart contracts before the programmers deploy them on the blockchain platform. And nowadays, there are two mainstream verification methods, the static verification and the dynamic verification. For the static verification, even though it can provide strong guarantees, it burdens the developers by developing exhaustive and meticulous specifications. And let's look at this smart contract example, which is written in the pyTEAL language on the Algorand blockchain platform. And the pyTEAL language allows developers to write the smart contracts in a high level, and its syntax is similar to Python. And this example manages a list of 10 account balances and calculates the maximum balance. And in order to fully statically verify this piece of code, the developer needs to write the precondition and postcondition, requiring that the balances array is initialized and populated with non-negative integers. And for the for loop, the loop invariant is needed at the start of each iteration to ensure that the max balance must contain the maximum balance seen so far. And moreover, the process of updating max balance would use fold and unfold to reason about the parts of the array processed so far and the part that remains. And finally, a lemma would be used to prove that the maximum balance found is indeed the maximum of the entire array. And as we can see, the static verification has a large upfront specification cost. And besides, another disadvantage of static verification is that the unverified external code can break a contract's assumptions. The given example wants to handle the action of purchasing items. It calls another function in another smart contract to check whether the item is still available before each purchase. And in this case, this external contract may not be verified and may break the assumptions its caller makes. And since this behavior is undefined, it is difficult for the developers to write the complete and correct specifications. And on the other hand, for the dynamic verification, even though the techniques offer flexibility and ease of use, they can only uncover vulnerabilities in executed program paths at runtime. And also, they might increase the runtime overhead for weaker assurances. And besides, the runtime checks incur substantial transaction fees on the blockchains, increasing the monetary cost of executing the smart contracts. Fortunately, the Gradual verification allows developers to incrementally build up correctness specifications and proofs. And thus, the developers can focus on specifying and verifying the most important properties of their smart contracts. And the immediate verification feedback is a significant advantage of this approach. The Gradual verification supports static verification where possible and dynamic verification where necessary. And Gradual verification introduces a concept called imprecise specifications, marked symbolically as question marks. And these serve as placeholders. They represent unknown parts of a specification or combined with the known parts. And the verifier treats these imprecise specifications optimistically, but inserts the dynamic checks where necessary to maintain the soundness. The core of the Gradual verification is founded on separation logic, a form of logic that enables modular reasoning. And the simple explanation is that we can view the AND operator here as a separation conjunction. And the Gradual verification systems have three properties. The first one is soundness. Simply, if the verifier tells us it is correct, the static verification passes and dynamic checks do not fail, then the program is correct. And to elaborate on this topic, we could read Conrad's paper, which was presented yesterday. And the second property is gradual guarantee, which ensures that relaxing specifications should not introduce new static or dynamic verification errors. And the third one is a conservative extension, which says that anything provable in the base static system should be provable in the gradual one. Since our gradual verifier extends the base static verifier syntactically with gradual formulas, our system assumes non-contradictory strengthening of imprecise formulas. And thus, I will discuss the three significance of gradual verification in the context of smart contracts. So firstly, the gradual verification provides the balance between precision and flexibility. The developers start by writing partial specifications, providing the freedom to progressively strengthen these specifications over time. And moreover, the programmers can specify only the components they care about in smart contracts. Back to the previous example. If the programmers only care about whether the program's output is correct, they can only specify the preconditions and postconditions and add question marks in the looping variants. And after the program passes the verifier, they can then further complete the verification by specifying the looping variants and other parts like fold and unfold and the lemmas. And secondly, on the dynamic side, gradual verification can help reduce runtime overhead. The transaction fees and computational resources required for executing smart contracts can accumulate quickly, like the Ethereum gas fee, which increases with dynamic verification alone. And gradual verification minimizes this cost by minimizing runtime checks with statically available information. For example, in this simple code snippet, where we want to subtract a number quantity from the count value, we need to have 5 asserts with the dynamic verification alone. However, when we statically verify some of the properties, the number of the asserts is reduced. And when a proof obligation has been fully statically verified, no runtime check is generated for it. And therefore, the developers may choose to spend more time incrementally specifying their software to reduce the dynamic checking overhead. And finally, gradual verification can protect against unverified code and re-entrancy. When interacting with unverified external code, gradual verification can insert dynamic checks. And these checks prevent type violations and unauthorized access to memory, which unverified code might otherwise exploit. And re-entrancy attacks are a major concern in smart contracts. And these attacks will occur when a function calls an external untrusted contract, and the untrusted contract can then call back into the original contract. And this can potentially disrupt the state of the original contract. Gradual verification can mitigate such attacks by specifying the state invariants that must hold before and after the external calls. And gradual verification can ensure that the contract state remains consistent even if re-entrant calls occur. And next, I will discuss our gradual pyTEAL framework, which is used to gradually verify smart contracts on the Algorand blockchain platform. And the smart contracts are written in a language called PyTEAL. It is an assembly-like language, and it is processed by the Algorand virtual machine, AVM. And pyTEAL is another language that allows developers to express smart contract logic purely using Python syntax. It is high-level, and since the TEAL is low-level and complicated to write specifications, we choose pyTEAL as our target language to develop the gradual verification framework. And our model can be divided into two parts, the front end and the back end. In the front end, we converted the pyTEAL programs to Gradual CNOD, the only previously implemented gradual verifier. And internally, Gradual CNOD uses a variant of the Viper toolchain to statically verify functions, treating partial specifications optimistically. And then, the modified Viper backend generates the runtime checks wherever static verification cannot assure specifications. And these runtime checks are added to the original smart contract before compilation to the Algorand platform. And to be more specific, we construct a parser using the FastPass Scala library to parse the pyTEAL source code with specifications into an unresolved pyTEAL abstract syntax tree. And since Python supports the dynamic typing, but we're translating to a typed intermediate language, CNOD, we use type inference to assign the static types to all variables in the pyTEAL AST, resulting in an unresolved pyTEAL AST with inferred types. And we perform type checking and other well-formed checks, then translate the resolved AST to CNOD. And the CNOD AXT makes some operations more explicit, aiding some verification and connecting to the intermediate representation supported by Gradual CNOD. And during the static verification, the verifier optimistically interprets the imprecise formulas to satisfy a contract and denoted by the question marks. And this will be caused by the optimistic static verifier. And when those optimistic static verifier succeeds, a set of runtime checks are produced that must be executed at runtime for soundness. And we then identify the locations when the runtime checks should be inserted based on the placement of the question marks embedded in our pyTEAL specifications. And we develop the Weaver module to perform the step and encode the checks in the original pyTEAL program at the identified locations. And finally, the pyTEAL program with the runtime checks is transformed into an executable contract within the pyTEAL compiler, which is subsequently executed on the Algorand platform. And next, I will walk you through an example for gradual verification of smart contracts through the incremental improvement of specifications. And this piece of code depicts a selling transaction where a specified quantity is subtracted from a global state variable count. And it will start with the most imprecise form and then gradually refining them. Initially, we can place cross remarks in the contract specifications to indicate maximum imprecision. Assume that we only know our argument quantity should be more than or equal to 0, but we know nothing else about the preconditions and postconditions. And after we run the program, we will know that some dynamic checks will be inserted. For example, it will check the accessibility predicate to see if the program has the ownership of the count space. And since our verification is based on a resource logic, and so the predicates have to declare what global state they use. An accessibility predicate is a logical construct used in separation logic, which asserts that a specific memory location is accessible, enabling the modular reasoning about the state of that memory in a program. And then, before decrementing count, it will check if the count is sufficient to cover the quantity. This is to prevent underflow in a subtraction operation. And finally, after decrementing, it will check if the counts remain non-negative. And this is a standard check after an arithmetic operation that could potentially result in a negative value. And for the second step, we can elaborate our specifications and then reduce the dynamic checks. And finally, we could complete our specifications to pass the static verification and no dynamic check is inserted. And in conclusion, we talk about the significance of gradual verification for smart contracts. We talk about our current gradual pyTEAL framework, and we talk about the incremental gradual verification smart contract example. But our journey doesn't end here. Looking forward, our primary objective is to transition from the CNOT verifier to the independent verifier for smart contracts. And our next goal is to enhance the verification for smart contracts that involve external costs. And additionally, we plan to expand our set of runtime checks, specifically for the smart contracts. And finally, we're setting our sights on the ambitious goal of verifying smart contracts at the byte level. This is the end of my presentations. I'm happy to take any questions. Thank you.
Yeah,
Hi, thanks for the talk. I was wondering if how does your verification intersect with the gas metering? Like, is there anything specific you need to do? Can you do assumptions about gas consumption?
Yeah, so actually for the current step, our prototype doesn't support the estimation of the gas fee, but we know that in the specific context of the smart contracts, the gas fee is really important because when we execute the program on the blockchain platform, we need to pay the fees, the gas fees. So that in our future work, we want to include the estimation of the potential gas fee included to verify the smart contracts on the blockchain platform. So it is included in our future work.
Okay, thanks.
Other questions?
I'm wondering a bit about the first point here. Maybe you have said some things during the talk, but what are the advantages you gain by moving away from the CNOT verifier?
Yeah, so actually there are like three main reasons. The first reason is that right now we are like translating the pyTEAL language into CNOT. And CNOT is like a static type language, and pyTEAL is similar in syntax in Python. So we need to do the type inference. This is the first reason. And the second is that because I mentioned the global state, that is the heap locations that we need to check in our gradual verification system. But right now we need to manually translate the global state in pyTEAL into the structs, the data structure structs in the CNOT. And this is like another disadvantage for the CNOT gradual verifier. And also I mentioned, for example, the security permission. Like if we call the external contracts in our current smart contracts and we don't know the implementations of the external contract, we need to check the state invariant, for example, like what states are held or are keep consistent in before and after calling the external contract. And this isn't supported in the CNOT gradual verifier. So we want to elaborate on this to include more specific implementations of the security permissions with regards to smart contracts. And this is the second reason. And the third reason is that for the gas fee, because right now gradual CNOT doesn't have anything related to the estimation of the transaction fee, but like it is important with regards to dynamic checks on smart contracts. So we want to include this in our future work. Yep.
I have a question. Mm-hmm. So what kind of invariants has one to write to prevent re-entrancy?
So for example, like the state invariants, and secondly, for example, the resource ownership. Like when we do the transactions in the smart contracts, there might be something changed before and after we call the external calls. And in that case, some states might be some states should be unchanged and some states should change within our within our requirements, so that we can explicitly specify the state invariance and the resource ownership in our specifications to verify the smart contracts.
Actually, related to that, can those be statically checked? Like re-entrancy invariants can only be dynamic, can they?
Yeah, so the re-entrancy calls include some of the recursive calls in the smart contracts. And I do think for some of the state invariants, if we design carefully, I think some of them might be statically verified, but I'm still not sure because it isn't implemented in our current work. But I do think we need to consider that in our future work, yeah. So maybe the dynamic checks are only considered with regards to the re-entrant calls.
Yeah, because I'm thinking you have a contract that does a callback that is perhaps not even verified. It's outer code, so you have no way of knowing that piece of code is not going to re-enter back. At that point, when you're verifying the contract, you need to insert a dynamic check because you don't have the other code, right? So,
exactly.
yeah.
Because for the re-entrant calls, because we don't know the implementations of the external calls, so that you think that we cannot statically verify that because we don't know the implementations, but we can specify some of the state invariants. For example, before and after the calls, some states might be unchanged and some states might be changed according to our requirements, right? So that we can specify them in our static verification framework.
Cool. Okay, looking forward to seeing more of this.
Thanks.
I had a question myself. So there was a talk at Popple about, if I remember correctly, soundness of C0.
Yeah, exactly.
Is there any hope of using that to get provably sound, provably safe, or provably correct smart contracts?
Yeah, of course. So actually what we're using now is the Gradual C0, as you indicated in the presentation yesterday. So we use the exact same base Gradual verifier. And based on this C0 Gradual verifier, we built our own Gradual pyTEAL framework. So actually, we need to further guarantee our Gradual pyTEAL framework, but it is based on the Gradual C0, just as depicted in the presentation yesterday. Yep.
Thank you. So with that, I think we should pass the floor to Gregory. Maybe if there's a final question while Gregory sets up.
So I was wondering what happens when runtime assertions fail. Do you always just stop, or do you attempt to make sure there's some kind of liveness to these contracts?
So you mean for the dynamic or the static verification?
The dynamic checks.
Yeah, so actually we're compiling them through the TEAL compiler, and after that we run the smart contracts on the Algorand platform, and if there are dynamic checks failed, there will be an error message pop out.
Yeah, does that mean that resources can get stuck? If you have some money in a contract and then you can continually fail the contract, it might never get out.
I think right now we haven't tested, but I think this is a potential problem that we need to consider in our future work.
Okay, thanks.
Thank you.